Next type of matrices is row echelon form, or in short, we call it REF. So to make sure that that matrix is called REF matrix, make sure that it must satisfy these three conditions. Okay, so the first one, make sure that rows consisting entirely zeros occur at the bottom of the matrix. So if you have these matrices, okay, this is the diagonal matrix. Okay, so all the zero entries occur at the bottom here. Okay, so it occur at the bottom. This is what the first property say. Entire rows consisting entirely zeros. Okay, so this is the rows where it is all zero, and this is all zero, must occur at the bottom of the matrix. So at the bottom of the matrix. Okay, so this is the matrix and this is the bottom part lah. Okay, so entirely zero means the bottom here. Sorry, this is all entirely zero. Okay, it occur at the bottom. Right, so the second property, for each row that does not consist entirely zeros, the first non-zero is 1. Okay, so this is, let's say you have, oh sorry, 0, 0, 0. So this is the bottom part, be 0. So this is 0. Okay, so the first number after 0 must be 1. Okay, so the first non-zero is 1. The first non-zero, so this row, okay, is not entirely 0. Okay, it's, so the first non-zero must be 1. Okay, this is what it means by the second properties. Right, so the third one, for each non-zero row, number 1 appear to the right of the leading one of the previous row. 0, 1, 2, for example, and 3. And then 0, 0, 1, 1. And this is 0, 0, 0. Okay, this is matrix 4 by 4, right? Okay, look at this matrix. I name it A. Okay, for this matrix, rows consisting entirely 0 occur at the bottom. Correct or not? Correct, because all the 0 entries occur at the bottom. Okay, at the bottom. It cannot be in the middle. It cannot be at the first row or the previous row. It must occur if it is all entirely 0. Okay, the entries are entirely 0. It must occur at the bottom. So satisfy the first condition, the first property. And then for each row that does not consist entirely 0, so if you look at the row, first row and second row here, these two rows are not entirely 0. It contains 0, but the entire rows are not 0 because you still have numbers, right? Alright, so the first non-zero is 1. Right, this is 0, fine, this is 0, fine, but the first non-zero, okay, this is not 0, right? Okay, it must be 1. So it means after 0, it must start with 1. Okay, same goes to here. After 0, it must start with 1. You cannot start 0 and then 2. Okay, this is not satisfy the second property here. But this, yes, this is the first non-zero is 1. Okay, so the third property, for each non-zero row, number 1 appear to the right of the leading one of the previous row. So the first row, it is fine to start number 1 here. Alright, but the previous, the next row, okay, depend on the location of number 1 of the previous row. If number 1 of the previous row is here, so the next row, number 1 must appear to the right. Okay, so number 1, the previous row must start the right of the leading one. of the previous row. So see, this is 1. So the next row, number 1 must start here. Okay, it cannot be below, it cannot start number 1 here. Okay, even though the first non-zero is 1 here, satisfy the first, but it does, it satisfy the second condition, but it does not satisfy the third one, because this one must appear at the right of the previous row. Okay, look at the example here. Alright, so A here. Okay, check the first condition where the first the row that consisting all the 0 entries must occur at the bottom. Correct? So satisfy the first condition. Okay, the second condition, for each row that does not contain all 0 entries, okay, the first non-zero must be 1. Okay, so this is non-zero entries, right? Okay, this is non-zero entries. So after 0 must start with 1. Okay, so check second. Okay, this is also fine because this is entirely non-zero. Okay, element. So it does not start with, so the first non-zero stay 1. Okay, still satisfy the second condition. Now look at the third condition. Must make sure that the number 1, okay, appear to the right of the previous. So the first row, this is the first row, second row, third row. So this, you can neglect this because this is entirely 0. No problem with this. Okay, but second row, okay, number 1 of the second row must start at the right of the previous row. So it depends to the location of number 1 from the first row. Okay, so since number 1 of the first row is here, so the next row, number 1 must start at the right. So at the right, it cannot be right under 1 here. So number 1 cannot start here. If number 1 start here, it does not satisfy the third condition. Since number 1 start here, yes, it is to the right of the previous row, which is the first row. Okay, so this is our REF matrix. Okay, look at B here. Alright, so B, property number 1, if there is non-zero, it must occur at the bottom, right? So since there is no non-zero, so that's fine. So we can skip the first property because it said if any. Okay, if any, it must be occur at the bottom. Right? Since in this matrix, you have no non-zero entries, so that's fine. Number 1, properties is considered pass. Right? Right, so the second property, where if the row does not consist of non-zero, after 0 must start with 1. So look at the non-zero entries. So 0, after 0 is 1, correct? 0 here, and after 0 is 1, check. And you have nothing here, but it must start with 1 because it says the first non-zero must be 1. Okay, so second condition, check. Okay, satisfied. So look at the third condition where number 1 must appear to the right of the previous entries. Okay, previous rows. Okay, so since 1 start here, the next must start at the right of the previous. So this is the right of the previous. This is also number 1 also start on the right of the previous. So this is matrix B is also REF. The last types of matrices is reduced row echelon form, or in short we call it RREF. Okay, so RREF, we have one additional condition or properties to the REF form. Okay, so it makes RREF matrix. Okay, so the first condition or the first property remain. Okay, remain means similar to REF. Okay, if there is entirely zeros, it must occur at the bottom. And the second properties also remain, means the number one must start after zero. Okay, number three, the third properties, if each non-zero rows, number one must appear to the right of the leading one of the previous rows. So this is similar to REF. Okay, one more properties. Okay, adding to the REF form, which make this matrix differ from RREF. Differ from REF is make sure if a column contain a leading one, then all the other entries in the column must be zero. Okay, must be zero. So these three properties, when you satisfy, it become REF. Okay, if you add one more property, which is this, okay, it will become REF. Okay, where once you have leading one in that row, so the next entry after that must be zero. Let us look at the example. Okay, look at the matrix A here. Okay, so check the first for RREF. There are four properties. Okay, four properties. So number one, check if there is a non-zero rows. Okay, it must occur at the bottom. Yes, yes. Okay, and then the second one, for each row that does not have zero entries. Okay, the first non-zero must be 1. Okay, so means after 0 must be 1. 0, 1. So this is fine. This is also fine. So the third one, number 1 must appear to the right. Yes, the number 1 here appear to the right of the previous. So this is non-zero, so it's okay. So one more condition to make this matrix become RREF is if the column contain a leading one. So we look at column by column. If it contain leading one, okay, leading one mean this, or the diagonal is leading number 1, so it is leading one. Okay, look at this column. Yes, it has leading one. So the rest of the column and the entries of the column must be 0. So 0, 0. So check. Look at second column. Okay, do you have leading one? Yes, you have over here. So make sure that the rest of the entries are 0. Yes, it is. Look at the third column here. Do you have leading one? No, you don't have leading one here. Okay, this is minus 4, 7 and 0, so it's not necessarily be 0. Okay, so all the condition satisfied. Only whenever you have leading one for that column, the entire column must be 0. Okay, so A is RREF. Okay, so check the second matrix. Okay, this matrix is RREF. Let's go one by one, check the property. So is there any non-zero entries? No, we don't have any non-zero entries. Okay, so that the first condition, the first property consider pass. Alright, so the second property, make sure if there is the first non-zero must be 1. Yes, the first non-zero means the after 0 must be 1. It is. Okay, so second condition, second property satisfied. The third one, number 1 must appear to the left of the previous leading one. Okay, so yes, it appear to the left of this row, and this one appear to the right of previous row. So the third condition also satisfied. Now look at the fourth properties, where if you have leading one for that column, the entire column must be 0. Okay, check the first column. Do you have leading one? Yes, you have one here. So the entire must be 0. Okay, so check. So the second column, do you have leading one? Yes, you have leading one here. Okay, so the rest of the entire element must be 0. Okay, so check. Do you have leading one for column 3? Yes, you have at the bottom here. Okay, this is all leading one here. Okay, and the entries are all 0. Yes, check. So B is also R, R, E, F. So we have done with all the introduction and the types of matrices. Now we go to operation involved in matrices. Alright, so the first one, I will talk about the addition and the subtraction of matrices. Okay, I have explained this before. Okay, at the earlier slide. Okay, the addition and subtraction of two matrices can only be performed whenever the order of the two matrices are equal. Okay, so you must make sure that matrix A must have m times n. To add with matrix B, they must have n times n. Okay, so they must have equal order. If m is 2, matrix B also must have m equal to 2 by, if this is 3, your matrix B also must have 3 column. Okay, once they have equal row, equal column, you can add the two matrix. Same goes if they have two subtraction of two matrices. Okay, so this is a definition for subtraction. So I don't want to read this. Okay, I just want to explain this in a simple way. Okay, we don't need to depend on the definition as long as we know how these two matrices, okay, can react to each other. Okay, so you don't need to remember the definition. Okay, so you just need to make sure that they have equal order. Okay, and then you can perform the subtraction and addition. So this is the property of addition and subtractions. Okay, so this is just a common um, operation that we perform involving the subtraction and the addition of two matrices. Okay, they are equal to whenever we to the addition or subtraction of the numbers. Okay, so if you have matrix A plus matrix B, you can swap the position. Okay, you can add the B with matrix A. Okay, so if you have the bracket, okay, for addition and subtraction, okay, you can start with A plus B, okay, first, and then followed by addition to C, matrix C. Okay, but not for multiplication. If for multiplication, you must follow the orders. Okay, so bracket first. All right, for addition and subtraction, it doesn't matter. All right, so for matrix A, if you add with a 0 matrix, you get the matrix back, and if you add the matrix with the negative matrix, you get 0. Okay. Alright, in this definition, it just explain about the scalar multiplication, okay, where you have a scalar that you denote as alpha here. Okay, this is similar to k just now. Okay, in the previous slide, you have k, we denote as a scalar. So here, we just change the notation to alpha, where it is similar to k. Okay, so alpha is also a scalar, when you multiply scalar alpha to your matrix, so each of the element in the matrix you multiply with the scalar. Okay, for example, you have matrix A 1 2 3 4 here, and then you have a scalar 2. Okay, your alpha is 2. Now 2 multiplied with A means you multiply each of the element in A here with 2. Okay, so 2 times 1, 2, 2 times 3 is 6, 2 times 2 is 4, 2 times 4 is 8. Okay, so each of the element of your matrix A you multiply with the scalar. That's it. Alright, so this is the property of a scalar multiplication. If you have matrix A, B, and C, as well as the zero matrix here, where all the matrix here is a m by n matrix. Okay, when you need to perform the scalar multiplication to addition of matrix A and matrix B, that is equal to you multiply the scalar to matrix A first, and then multiply scalar to matrix B, and then after that you add. Okay, same goes to this. Okay, you have addition of two scalars, scalar alpha and scalar B. Okay, that is equal to you perform this operation. Okay, scalar A multiply to matrix A plus with scalar B multiply with your matrix A. Okay, when you have multiplication of two scalar times the matrix, that is equal to you multiply one of the scalar to A first, and then you after the product you multiply with the second scalar. Alright, so if you have matrix identity, you multiply with matrix A, that will give you matrix A again. Okay, and when you multiply A with a zero matrix, you get zero matrix. Okay, in this definition, it explains the condition. Okay, for matrix A and B, multiplication of matrix A and B to exist. Okay, so as I explained before, okay, in order to say that matrix A and matrix B can be multiplied, make sure that you have the column for matrix A is equal to the row of matrix B. Okay, so here let's say A is a matrix of order Mn. So this is row, this is column. Okay, you have matrix B here with order PQ. Okay, this is a row of second matrix. This is column of the second matrix. Okay, in order for multiplication of A and B to exist, you must make sure the column of matrix A equal to row of matrix B. So make sure your N equal to your P, then A and B exist. Okay, multiplication of A and B can be done, and the product is expected to be a matrix with order row column. So row is M, column is Q. So it should be matrix. Okay, so the product should be M by Q. Okay, this is expectation of the order for the product. If N and P are not equal, so you cannot perform multiplication of A and B. Okay. This is the property of a matrix multiplication. Okay, so the first property, it follow the distributive law, where when matrix A multiply to the addition of matrix B and C, okay, that is equal to you add matrix A times matrix B with matrix A times matrix C. Okay, this is distributive law because you distribute EB plus EC. Okay, same goes to matrix B plus matrix C, that is equal to B plus multiply with A, okay, plus C multiply with A. Alright, when you have three multiplication of multiplication of three matrices, okay, that is, you can do A times B first and then multiply with C. That is called associative law. Okay, associate. Alright, and the multiplication of scalar to the multiplication of matrix A and B. Alright, that is, you can do the multiplication of the scalar to one of the matrix first and then multiply the rest. Let us proceed to example. Okay, first before we proceed, let us check the order. Okay, the order of the matrix A and B. So the order is 2 by 2, matrix B is also 2 by 2. So since they have the same order here, okay, so column equal to the column, row equal to the row, sorry, row first, row equal to the row of matrix B, row column of matrix A equal to the column of matrix B. So you can perform the addition. Alright, so to perform the addition, okay, you must add entry, the first entry with the first entry, second entries with the second entries, and so on. Okay, so this is equal to 4 plus 5, 3 plus 8, 1 plus 9, 2 plus 7. Okay, so you will get 9, 11, 10, and 9. Okay, so subtraction here, you need to multiply the scalar 2 to A and scalar negative 3 to B. So you do that. 2 to matrix A, so you get 8, 6, 2, 4, multiply with 3 times 2B, that is 15, 24, 27, 29. Okay, so you subtract first entry with the first entry, 8 minus 15, that is minus 7. 6 minus with minus with 24, that is minus 18. 2 minus with 27, that is minus 25. 4 minus with 21, that is minus 17. Okay, so A multiply with B, we must check the column of the first matrix must be equal to the row of the second matrix. Yes, they are equal. So A and B is possible. Alright, so to multiply this, 4, 3, 1, 2, B is 5, 9, 8, 7. Okay, let us multiply. So since this is 2 by 2 with 2 by 2, okay, so they are equal, right? So you should expect the product of A and B is 2 by 2 matrix. Alright, so you need to prepare 2 columns, 2 rows. Okay, so first, change the color. Okay, we take this row multiply with this column. So 4 times 5. Okay, plus with 1 times 8. Okay, so this is first row, first column. So the multiplication of this first row, first column will be the first row and first column punya entries. Okay, right, so do for second column. Okay, you do for second column here, still the first row. Okay, so still the first row, but second column, which is here, we start new entry for this. Okay, so 4 times 9 plus 1 times 7. Okay, now we have the first row and the second column. First row, second column. Okay, let's move to the second row. So now we are going to create second row, first column. So where is second row? Second row is here. First column where? This is first column. So the product of second row, first column should be here. Okay, so 3 times 5 plus with 2 times 8. Okay, so we're done. Now we proceed to second row, second column. Where is second row, second column? Stay here, second row, but second column is 1, 2 is here. So we are going to start new entry here. Okay, so 3 times 9 plus 2 times 7. Okay, then we solve this. 20 plus 8, 15 plus 16. This is 32 plus 7, 27 plus 14. So the product is, I continue here, 28, 31, 39, 2, 3, 4, 1, 41. Okay, so this is matrix A, B. As we expect at the beginning, it is 2 by 2 matrix. Alright, next, the fourth is AB transpose. So we have the AB product here and we need to transpose this. So AB transpose is equal to column become row, 28, 31, 39, 41. Done. Alright, so this is the answer for the previous example. Oh, I just realized that I made a mistake here. 3 times 9 is 3 times 9. No, 4 times 9 is 36. But what I did just now, 4 times 9 is 32. Okay, please do the correction, alright? So 32 plus 7. 32 plus. Okay, so if we make the correction, 36 plus 7, that is 43. Alright, 43. Okay. So I guess that's it for part 1. Alright, so what we have done, alright, is just a recall to the matrix. You have learned about all these operation type of matrices in your previous level. Alright, so hopefully this recalls back all your memory skills and knowledge. Okay, refresh up everything. Okay, freshen up everything. And then I guess you can start doing your tutorial. Okay, number 1 to number 6. Okay, tutorial 2, number 1 to number 6. Thank you very much. I see you in the next lecture, part 2. Assalamualaikum.